Using Laplace, what's my x of s? Take a look at my waveform over here. And Chow, I haven't heard from you. Tell me what the Laplace transform of x of s is. And so what's the transform of this?
S 1 over S.
If it was just a u of t, it's 1 over s, but if it's times e to the minus t, it's
plus 1.
That's it. And similarly, we can do it for h of t, right? If I'm telling you that my h of t, I'll do it on the other side. If I'm telling you that my h of t is u of t, then Joe, tell me what, Joseph, Lieber, tell me what our h of s is.
That would just be 1 over s.
So therefore, you can tell, it's easy to find out what our output is. It's just our input multiplied by our h of s, which is going to be 1 over s times s plus 1. But you know from what we did last class that that's equal to some simple number over s plus some simple number over s plus 1. What is it over s? Use the cover-up method. The associated root for s is 0, so cover up your s, and you're left with 1 over 0 plus 1, which is 1. To find out the root up here, to find out what the numerator is up here, use your associated root, which is minus 1. Cover up your s plus 1 and plug in your root. That gives you 1 over minus 1, which is minus 1. So that's 1 over s minus 1 over s plus 1. And now, who's next in line? Jonathan, tell me can you remember this off the top of your head? What's the inverse transform of this whole mess? What's the inverse transform of 1 over s?
The inverse transform of 1 over s, I'm pretty sure it's just u of t.
That's it.
And 1 over s plus 1. I can't remember that one off the top of my head. I think it's something like maybe like e to the negative t.
Yeah, u of t, that's it. And of course, we can factor the u of t's out just to make it 1 minus e to the minus t u of t. So 2 ways to do it. Exact same answer. Which would you rather do?
The second one.
Yeah, holy cow. So that's why we choose this whole Laplace method, because it's so much easier than convolution. So you might even wonder, why do we even teach convolution if we can just use Laplace and get around it? And it's because Laplace is easy for us because we can use heuristics to do Laplace transforms. It's really hard to teach computers how to do Laplace transforms. But when you take a look at what the definition of convolution is, it's just a summation. We can replace this integral sign with a summation sign and do lots of little summations all over the place. Computers are great with that. So if we were to program a computer to solve this repeatedly, and we do, anytime you've got, say, all kinds of systems, the one that just comes up to my mind because we were just talking about a military example is a missile guidance system. And it knows where it wants to go. It has to put its desired trajectory into the system, which then changes its desired trajectory into a fin position, a control surface position to get there. And it does not take Laplace transforms of the input versus its impulse response of its system. It does this convolution operator at high speed. So that's why we teach both. There's one last skill I'd like to go over, and that is we've certainly done math, we've done Laplace. The only thing is we haven't done graphically. I did a very hand-waving graphically thing here. But let me